In this video, we're going to be starting our discussion of area under the graph of a function. And specifically, we're going to be kind of learning about the idea of a Riemann sum. And so I'm just going to show you these two graphs here. And they've both got shaded regions underneath them. And I'm just going to show you that, it's kind of going to come down to two cases, at least in this video. We're going to have the ones that we can find the area of using geometry formulas, like the one on the left, since the graph is formed of a line and part of a circle. And then we've got the ones on the right, they're curved. We don't have a geometry formula for the area under the graph of an exponential function. So we're going to need to use calculus for that. And that's what I'm going to spend the next few lessons developing with you. And the notation you're going to see for the area under the graph of a function between x equals a and x equals b is going to be right here, the integral from a to b of f of x dx. And the fact that that uses the same notation as the antiderivative, it's not a coincidence, and the connection there is what we're going to be looking at in the next lesson. But for now, we're just going to be content finding some areas. So we're going to say, all right, what we're going to do here is we're going to kind of chop this up into some subregions. All right, so the stuff to the left of that red line, I could look at that either as a trapezoid or as a rectangle plus a triangle, and I'm going to recommend in this class that, there's going to be times where we have to use a trapezoid, right, and that'll even be, later today. But, sometimes we can just make our lives a little bit easier, and I'd say just, do the rectangle and the triangle. So this one's 3 times 2 is 6. You can even see there's 6 squares there. And the area of the triangle is going to be 1/2 times 3 times 3. That's going to be 9 halves. Okay, and then we have the stuff to the right of the red vertical line. Well, we can definitely block off that bottom part and say, hey, that's another rectangle right there. That's going to be another rectangle with area 6. And kind of save this for last. But I think you actually do know how to find the area of this little crescent-shaped region in there. The white area, kind of where the arrow is coming from, well, that's a quarter circle. And we could say that, okay, kind of like looking at that whole square there of 4, we could subtract off the quarter circle and have the area of our shaded piece right there. So that would be the area of the square is 4 minus the quarter of a circle. So that's 1/4 of pi times radius squared. It looks to me like the radius is going to be 2. And so if I was to simplify that, that would be 4 minus 1 pi. So if they ask me for the integral from 0 to 5 of f of x dx, what they really are asking me for is the area under the graph of f and above the x-axis between x equals 0 and x equals 5. And so we'll find that by just adding up all of the pieces that we found. So it's going to be 6 plus 9 halves plus 4 minus pi. And you could simplify that if you wanted, but I'm just going to move on. Now for areas that don't have a known formula, like that area under the graph of y equals e to the x that we saw earlier, we're going to approximate with a Riemann sum. And a Riemann sum for the area under the graph of a function and above the x-axis for that integral is given by this formula here. And, it's a series, and, it might look a little intimidating, but I translated it down below. So it's the sum of heights times widths. It's the sum of the area of those rectangles that I had drawn earlier. Alright, so let's do a couple of these. So we're going to approximate the value of the integral from -1 to 1 of 4 to the x using a Riemann sum. And so I think it's probably important looking at the graph. Yeah, the graph goes from x equals -1.5 to +1. So we should, be aware that the limits of the area we're interested in are right here. So I'm not going to be interested in anything outside of this. Alright. So for this left Riemann sum, I'm going to do it with 2 subintervals of equal width. And you'll always be instructed in the statement of the problem on how many subintervals to use, if they need to have equal width, and which type of Riemann sum you're going to do. So kind of the first step is to subdivide your interval. We're going from -1 to 1, that's a width of 2, and 2 subintervals would just be dividing it in half. So it's going to be like right along here. And then if it's a left Riemann sum, we use the left edge of our subinterval as our representative. So I'm going to go right here to the left edge of this first subinterval, right? Here at -1. I'm going to use the height of the graph right there for the height of my rectangle. I'm going to go over here and I'm going to go down. And okay, got a rectangle. It's not very big. Okay, and then for the second subinterval, that's from x equals 0 to x equals 1, x equals 0 is on the left side, so I'm going to use the height of the graph here to approximate. We can see that this is not going to be a very good approximation, right? Like, it's going to be actually pretty terrible. It's way underestimating the true area. But all the same, sometimes we're asked to do these things, and we're just going to do them. We're going to figure out the value of the total of these, kind of like these areas here. So the width of each of them is 1. So the first one has width 1 and height. Well, I can find that by taking 4 to the x. So that was 4 to the -1. And then I'm going to add, okay, the second one had width 1, and the height was pretty clearly 1. Okay, 4 to the -1 is 1/4, so 1 and a fourth, that's going to be 1.25. Okay. And then for the right Riemann sum, let's do that one with more subintervals. Let's do that one with 4 subintervals of equal width. All right, so I'm going to subdivide my interval from -1 to 1 up into 4. So 1, 2, 3, 4. And then if I'm doing a right Riemann sum, I use the right edge of each subinterval, right, for my heights. So I'm going to have one here, one there, one over here, and one right here at that's not where that should intersect, is it? It's 4 to the x equals 1, that should happen right there. Okay, so then I'm going to, make my rectangles. Keep going, all right, and then I'm going to add those up also. Okay, and so I'm going to have each of them is going to have a width of 0.5. The height of the first one was 0.5. The height of the second rectangle is 1. The height of the third rectangle is 2. And the height of the fourth rectangle is, what's that, 4. Yeah, because it's 4 to the first power. Okay, now, and, in the free response questions, which these oftentimes come as free response questions, we are clear to just, leave it unsimplified, as the sum of things multiplied together. In fact, that's actually probably going to be the way for us to go. It's going to be at least risky, thinking about strategy for AP Calculus, but I'll have more to say about that, as we move forward. Okay, so I also need to tell you about a midpoint Riemann sum, and this one's pretty rare, but, it's in every Cal 1 textbook, and it is potentially testable for AP Calculus. So what we're going to do is we're going to use a midpoint Riemann sum and 3 subintervals of equal width to approximate the integral from 20 to 80 of r of t dt. And so I'm going to point out that that's going to be 20 to 80 right here. Okay, so we want the area under that curve. Okay, and what I'm going to do is I'm just going to show you what I mean by midpoint Riemann sum. So I've got 20 right there going to 80 and 3 subintervals. So that'd be 20, 40, 60, 80. Okay, dividing it up like that. And the midpoint for each subinterval would be halfway in between. So it'd be 30, 50, and 70. So what we're really interested in is the height of the graph at 30 and 50 and 70. And so the midpoint Riemann sum will do a little bit better as far as the overestimating and underestimating than the left and right. But in practice, they're oftentimes really hard to compute, or you don't really have the right data to compute them. And there's actually an even better, more accurate approximating technique that we'll show you next. So midpoint Riemann sum kind of gets forgotten about sometimes, but that's no big deal. Doesn't mean we're going to forget about it. We will know how to do it. So I'm going to think about basically the first subinterval is from 20 to 40, right? And we're going to use, and then we'll draw 60 in as well. Okay, we're using the midpoint as our representative. So our rectangle, kind of looks like that. And so we're using 30. But the width of the subinterval is from 20 to 40 is 20, and the height was 30. Plus, then over here at t equals 50, it says that r of t is 55, so 20 is the width and 55 is the height. I can draw that also. Okay, and then at t equals 70, r of t is 65, so 20 times 65, and I can draw that in there. And we see that's a much more accurate approximation for the area. Okay, I've got my three subintervals, width times height plus width times height plus width times height. Okay, and so we've approximated that integral that way. And if we've got a calculator on us and we need to do something else with it, then it might help simplify, but in general it does not. It's only an opportunity for an arithmetic error and for you to lose credit. Okay, what are the units of measure for the integral from 20 to 80 of r of t dt? Now, that's something new for us, right? We haven't really talked a whole lot about area in this class, and kind of just danced around it a little bit. The units of measure for the area, if I've got, let me just go in, this is not going to be a representative piece, but if I had a unit square over here, say it was 1 unit wide, time in minutes. That's a little too wide, but and then rate of fuel consumption, they gotta give me gallons per minute. Okay, so that would be gallons per minute. Okay, and if we multiplied those, we would get gallons, right? And that's what you do to find an area, so you could multiply the units and find the same thing. And so that's what I would say over here, is that r of t is in gallons per minute, dt is in minutes. We're adding all of those up, okay, adding up a bunch of heights times widths, and the minutes are going to cancel, and that's going to equal gallons. Okay, and then, letting the units guide our interpretation. What's the meaning of the integral from 20 to 80 of r of t dt in the context of the airplane's flight? Okay, well, an airplane burns fuel at a rate of r of t gallons per minute. Okay, and if we had a rate in gallons per minute, and then we had calculated a number of gallons, that's probably going to be the number of gallons of fuel the airplane burned. And so a nice response to this question in the context of the airplane's flight: the amount of fuel in gallons burned by the airplane between t equals 20 and t equals 80 minutes. Now, I will point out that a lot of the questions that are like this for AP Calculus ask for you to include units of measure. And so that's where the part where I said in gallons and t equals 20 to t equals 80 minutes is really important. Oftentimes people will remember to mention the gallons, but forget to mention the units of the independent variable, which sometimes can cost you. So don't forget about that. I just figured I'd start reminding you from the beginning. All right, the last type of sum I've got for you is the trapezoidal sum. And this one is by far the most accurate, and it's also a little bit more, time consuming to compute, especially if the numbers are not easily averageable. Okay, but I think first I need to remind you about how to find the area of a trapezoid. All right, so you may remember from geometry class that if you've got like base 1 and base 2 of a trapezoid, and it's got this height h, that the area is equal to, you average the bases, so base 1 plus base 2 over 2, and then you multiply by the height. But we're not going to really be looking at trapezoids that look like this in calculus. It's going to almost always look like this, right? Because it's going to be, two heights of a function, and we're going to average those heights and multiply by the width. And so I'm just going to, say that's h2 and h1. But the principle is still the same. We're still going to say area is going to be average the heights, or the bases really is what they are, h1 plus h2 over 2. And then we're going to multiply by the width of the subinterval. So if we are using a trapezoidal sum and subintervals indicated by the data in the table to approximate the number of liters of water that are pumped into the tank between t equals 1 and t equals 8 hours, what we're going to do is kind of start with our widths. Okay, that's what I would recommend doing. Okay, so this one has a width of 1. Yeah, from 0 to 1, from 1 to 3 is a width of 2, 3 to 6 is a width of 3, and 6 to 8 is a width of 2. So I'm going to have 1 multiplied by something plus 2 multiplied by something plus 3 multiplied by something plus 2 multiplied by something. Okay, so those are the widths, and we're multiplying the widths by the average of the heights. And so, I mean, if you can just think of the average of 1340 and 1190, I mean, good for you, right? You've got good arithmetic skills. But if you can't, we're just going to write add them and divide by 2. So 1340 plus 1190. It's definitely plus, not minus, right? If we want the average of these two things, we add them all up and then we divide by the number of things there are. It's going to be something we talk more about in this unit. Okay, and then I'm going to do the same thing, 1190 plus 950, and you get the idea here. For the subinterval from 3 to 6, the one with width 3, I'm averaging 950 and 740. Plus 740. And then for the last subinterval from 6 to 8, I'm averaging 740 and 700. And this is nice because it kind of takes into account all of the function values in the table rather than just all but one, right? If we used a left Riemann sum or a right Riemann sum, we would be necessarily ignoring one of these values from the table. Okay, and so this is a trapezoidal sum approximation for the number of liters of water, which we could find by taking the integral of r of t between t equals 0 and t equals 8. Okay, and I am recognizing, okay, I fell into my own trap, okay, but just in time. Okay, notice here, they said between t equals 1 and t equals 8 hours, right? So we really wanted to start our sum here and end it there, which means that this stuff here from t equals 0 to t equals 1 is not helpful, and in fact it's wrong. So we would need to get rid of that, if we wanted to be correct. Okay, but it's easier to erase than it is to add something that you don't have. Okay, glad I caught that though. Alright, now before we go on too much farther, I am going to give you the true definition of the definite integral. That's what that is, the integral from a to b of f of x dx. The exact value of the area of the shaded region, or I mean it's usually shaded, but the region between the graph of y equals f of x and the x-axis is given by the limit of the Riemann sums as the number of rectangles goes towards infinity. And, their respective widths go towards 0. Okay, and the actual details of that are something that we will investigate a little bit in this class, but are kind of more of the topic of an analysis class. Okay, but you do need to understand the idea of the exact value of the area being the limit of the Riemann sum. I found that understanding comes with time, though, so let's just move on and talk about something else. We're going to discuss if a Riemann sum is an overestimate or an underestimate. So the question is, does a left Riemann sum overestimate or underestimate these integrals? And we're going to give a reason. So I'm going to draw you a picture of these graphs. So integral from 0 to 4 of square root of x dx. All right, and my recommendation when you're making these determinations is that you, oh, whoops, I forgot to get my cover sheet off, is that you do fewer subintervals. Fewer is going to be better. Fewer will allow you to really clearly see whether it's an overestimate or an underestimate. So if we're going to do a left Riemann sum, I'm just going to divide it into two subintervals. I'm going to use the left edge of each to approximate the value. Okay, and we can see pretty clearly that this is going to be an underestimate. Okay, so I'm going to say underestimate, and I'm going to hope that the same thing applies for e to the negative x. Okay, oh, whoops, no, it's not going to be. Okay, so I'm going to say under here. For e to the negative x, and we don't need to know like a whole lot of specifics about the graph of y equals e to the negative x, besides that it just is exponential decay. And I guess from 0 to 2, it comes in like that. We don't really need the stuff to the left of the y-axis. Okay, so if I'm going to use a left Riemann sum, I'm going to go and I'll divide it into two subintervals, and I'll use the left edge. I'll see that I'm overestimating the true amount of area under the graph of e to the negative x between x equals 0 and x equals 2. So I'm going to say that this is an overestimate. Okay, and my reason is going to be the increase-decrease behavior of the function. I'm going to say that square root of x is increasing. That's the cause, if you think about it, if you draw yourself some pictures of different types of increasing functions. And the fact that the left Riemann sum overestimated the integral from 0 to 2 of e to the negative x is the fact that e to the negative x is decreasing. It doesn't have to do with the concavity for a left and right Riemann sum. Right there. Okay, well, yeah, we'll do the same thing for a right Riemann sum. I'll do this one a little faster. All right, so if I sketch these graphs and I, make a little right Riemann sum with two subintervals, I'll see again on the left I've got an overestimate, on the right I've got an underestimate, or maybe that's the opposite of what I saw last time. Yeah, it probably should be. But the reason for these is, again, the increase and decrease behavior. If you think about it, if you draw yourself some pictures, you can commit yourself. And if you can't commit yourself, come talk to me and I can convince you with some pictures. Okay, and then the other thing we have to think about is trapezoidal sums. And I'm going to draw these graphs for you. And for these, I'm going to actually recommend you just do one subinterval, because the trapezoidal sums are pretty accurate. And we're going to need to really be able to clearly see, maybe I'm saying that's x equals 1 right there, the right edge. If I make a trapezoid, okay, those would be the two bases or the heights, whatever you want to call them. And then I'd connect right there. Okay, and we can see that the curvature of the graph is what's causing it to be under or over that straight line. And so we're going to say this one's going to be an overestimate because the amount of area in the trapezoid is greater than the amount of area underneath the graph. And the reason is that e to the x has a concave up graph. Okay, and if I go over here to the square root of x1, okay, integral from 0 up to maybe 4 is right there. If I connect those with a straight line, it actually ends up being a triangle, particularly if it's a trapezoid with one of the heights being 0. This one's going to be an underestimate. And the reason why is because the graph of y equals square root of x is concave down. Okay, now the last thing I got for you is a couple properties of the definite integral, and these just don't fit in very well anywhere else, so I'm just going to tell them to you right now, and we're going to need to use them every once in a while, and they connect to some pretty good problems in AP Calculus. So I'm going to try to draw you a picture to convince you of all these things, kind of a simplest case picture. Suppose we've got f of x right there. Okay, so the integral from a to b of f of x dx, whoops, right here. Okay, that'd be that area, plus the integral from b to c, which would be, this amount of area right here. We can say that's going to be equal to the integral from a to c of f of x dx. And that's really just the area addition postulate from geometry. Okay, the integral from b back to a of f of x dx. That's going to be the negative of the integral from a to b of f of x dx, and I think that the reason why is much easier to understand in the next lesson. You could think about the Riemann sum being that all of the subintervals, they have like kind of a backwards or a negative width, but I actually think it's just going to be easier to think about it next time when I show you the fundamental theorem and you can really understand why it's the negative. Okay, integral from a to a of f of x dx. Okay, that would be the total amount of area represented by that blue line right there, the amount of area under the graph of f and above the x-axis between x equals a and x equals a. And a straight line doesn't have any area, so we're going to say that's going to be equal to 0. And so the last thing we've got is that the integral from a to b of k times f of x dx, we can factor out the k. That's going to be k times the integral from a to b of f. You could think about this in terms of like a vertical dilation on the graph of f, or you could think about it, with the Riemann sum. 6 times the function, you could factor it out of the sum on each of the subintervals, and you could add those all together the same way. Either way, we are going to be able to factor a constant out of an integral, and we'll make use of that pretty regularly in this class. Now we're going to wrap up with some practice problems. So suppose regions A and C each have area 9, and region B has area 4. Okay, the integral from 0 to 11 of g of x dx. Oh, okay, yeah, I'm glad I got to this because I needed to talk about this, but I never know where to fit it in on a Riemann sum, Dave. Because generally the Riemann sum, functions that we're taking are always positive. Not always, though. So region A has 9, and C also has 9, and B has area 4. Okay, what I need to tell you is that if we're integrating from 4 to 7, those 4 units of area under the graph of G and below the x-axis, those are going to count negatively. That's when we said the net signed area. So the integral from 0 to 11 of G is going to be 9 plus a negative 4, because we're going to count those as negative areas below the x-axis, plus another 9. And that's another thing, that the reason why we're going to do that, it becomes much more obvious once you understand the fundamental theorem. So I'm going to have 18 minus 4 is 14. The integral from 7 to 4 of 2g of x. Well, I think the first thing to do would be factor out the 2. And then, okay, 7 to 4, that's backwards. So I'm going to reverse the order of integration, or I guess that's not really what I meant. Reverse the balance of integration, and that's going to make the integral negative. So the negative 2 times the integral from 4 to 7 of g of x dx, and that's going to equal negative 2 multiplied by, okay, that negative 4 right there. That's going to equal positive 8. And then the last one is the integral from 7 to 11 of g of x plus 1 dx. Okay, and then this is a little bit more challenging. So what we're going to do is we're going to split this up using that first property. We're going to say this is the integral from 7 to 11 of g plus the integral from 7 to 11 of 1 dx. Okay, I'm going to actually go in and zoom in on this a little bit. So right here, the integral from 7 to 11, that's going to be 9. I think we saw that that area was 9 from the beginning, and I think that's fine. We know that this one right here, that's going to be 9. But the integral from 7 to 11 of 1 dx, we're going to do that one with geometry for now. So actually, I'm not going to need a y-axis. Let's do an x-axis. Here's 7, there's 11. Y equals 1, probably up there. And if we're taking the integral of just 1, that's f of x equals 1 for all x. And so this is a rectangle. It's got height 1 and width 4, so that's going to be 4. And so the total of this integral is going to be the 9 plus the 4 is equal to 13. And below here, I've got some extra practice on recent free response problems, but these are all similar to problems that we've done in this video, and this one's getting a little long. So I'm going to save that for a different video, and just say thanks for watching. Hope it helped.